So, good morning everybody. We are getting into a new section in this course on motors and controllers. You have already covered a lot of ground in understanding about electric vehicles. You have understood overall about what are the components of an electric vehicle, in what way is it different from a conventional IC engine vehicle, and you have learnt about batteries, which are the equivalent of a fuel tank in the conventional vehicle, and what are the different challenges in designing a good battery pack for an electric vehicle. Now we are coming to what may be called as the engine, the heart of an electric vehicle, which actually powers the vehicle. How the vehicle performs is entirely dependent upon how the motor and together with its intelligence which sits in the controller, the performance of the vehicle entirely depends upon that performance. And I have heard in the past that it is a fairly complex and difficult thing for people to understand. I have tried to make the presentation as simple and lucid as possible, and I have by and large assumed that you do not have any prior knowledge other than high school physics, and from that level I will try to take you through it step by step. But I must warn you that I will start in a very simple way, but very soon if you are not alert, you will find that things have got pretty complex. You may have to re-watch the videos again and again before you get a grasp of it. So here we are. Let me start with giving you an overview of what all we will be covering. I will start with what you are already familiar with, vehicle dynamics, that Professor Jhunjhunwala has already given you a fairly detailed overview of, but we will look at vehicle dynamics specifically from the point of view of how it impacts the design of the motor and the controller. And having understood that, we will do a little bit background about the different physics phenomena that operate simultaneously to make the motor function. And the good thing about these phenomena is that while they are from very different domains of physics, from electromagnetics to electricity to thermal and so on, the underlying mathematics behind them is very similar. And so broadly I have clubbed all these phenomena under the term flow, and different phenomena when they are flowing are governed by similar rules, and if we understand those basic rules, then we can understand all these phenomena, and then we have to see how a motor will function when all of these competing phenomena interact. So sometimes people use the word multiphysics. It is a sort of intimidating sounding word, but it is actually quite simple. And then we will go on to understand concepts like power, efficiency, and after that we will open up the motor. We will open up the motor and see what really is happening inside it, how actually torque is produced, which helps you deliver the force required to pull the vehicle, and the torque is connected with how much power is, how much electricity is drawn, how much current is drawn, and in turn what causes the electricity to be drawn is the voltage, and the amount of voltage that leads to electricity production is governed by what is called the back EMF, which is thrown back by the motor back towards the battery, and that back EMF interacting with the voltage of the battery decides what speed the motor will run at. And then there is a neat framework through which all this complex phenomena can be analyzed. That frame of reference is called the DQ reference frame, direct and quadrature, and once we analyze phenomena in that frame, then we have to translate it back into the real frame of reference where everything is actually alternating, and we need to therefore understand a bit about how AC current works, how it is different from a DC current, and the battery itself is a source of DC power, but how can we use that DC power source called the battery to then deliver AC current of the kind that we need to drive the vehicle. And going forward, we will take a fairly close look at thermal effects. You must remember that not only in the electric vehicle, but in almost all domains of engineering, the most important cause of a design failing is thermal. Whenever an engineered product is designed to operate in a certain way, if either it is designed poorly, or if it is manufactured poorly, or if it is operated beyond its prescribed design envelope, almost the first thing you will notice is that things are getting hot, and if you ignore it, at some point the entire thing will break, it will stop functioning. So when we design something, it is very important that we keep in mind the thermal limitations about which we should be very mindful of. And finally, I will take you through a number of engineering considerations that we have to bear in mind when actually designing a motor, which will impact on its life, on its performance, on its silentness, and so many other factors. And before signing off, I will conclude the section by talking about some new developments which are at a nascent stage, which will become more prominent in the years to come. So here we go. Let us start with vehicle dynamics. You are familiar with forces acting on a vehicle, but at the risk of repetition, I will repeat them again, and you will soon understand why. The context or the flavor of revisiting topics that you already know is to reapply them to understanding the motor in better detail. So let me talk with what are called drive modes. When we ride an electric vehicle, it could be a car, it can be a two-wheeler, the vehicle is operated in many different modes of operation, and I will quickly take you through some of the common operating modes. Why I am talking about operating modes here is that in the case of an electric vehicle, what makes the motor design more challenging than for a conventional motor used in an industrial machine is that all the other motors generally operate at a set speed and they operate against a set load. A common example is that in all of our houses we are likely to have a motor that pumps water to the overhead tank, and it has a certain fixed flow rate, it will have to deliver a certain fixed power, it will deliver a certain fixed torque, and it will run at a fixed speed, and we know that if I keep the motor on for 20 minutes in the morning, my tank will be full, and if I keep it running for 21 or 22 minutes, the tank will start overflowing. It is very predictable, nothing will change. Even if there are some changes, those changes are not going to happen within seconds. Maybe there will be a change over an entire year, because after the monsoons the water table is at a high level, and maybe 6 months later when it is very hot and it is summer, the water table is lower. So there is a change in the load, but that change in load happens over the course of many months, not in the course of a few seconds. The challenge with electric vehicles is that steep changes in load and in speed happen within seconds, and the motor must be capable of handling this wide range. So I will take you through some of these examples. One is what is called the economical speed. The vehicle can be driven at a certain speed prescribed by the manufacturer. At a constant speed you can go on a level road and you will get good mileage, the vehicle will be in good condition, everything will be fine. That is called the rated speed. Cruising, the word cruising means my speed is not increasing or decreasing, I am going at a steady speed, and that speed is equal to the speed recommended by the manufacturer of the vehicle, the rated speed. And then there are cases where I want to go to a hill station from the plains. I may take 2 or 3 hours to reach the hill station. At that time continuously I am going uphill. I am going uphill. Even if you walk, you know that when you walk uphill you are running out of breath after some time. You breathe hard. It takes more load. The motor will similarly have to deliver that extra load, extra torque for many hours, maybe 1 hour, 2 hours, 3 hours. It has to continuously deliver this torque till you reach the destination, which is a hill station. And that is another mode of driving. The other thing is when I am going on a highway, the road is clear, the road is very good, the sides are fenced off, there is no danger of people or animals suddenly darting across, there is no heavy traffic, and I want to reach the next town as quickly as I can. So I go at the top speed which the vehicle is capable of, and I maintain that steady speed maybe for an hour, 2 hours till I reach my destination. So this is cruising at the peak speed. And then sometimes it happens that let us say I am in the basement car park of a building, I am a little luggage truck and they have loaded a lot of things which I should be taking to a nearby from this warehouse where I am loading everything. I have to take the truck to a shop where I have to offload the goods. And commonly what we will find is that from the basement car park, when I have to get out onto the road, already my vehicle is full of luggage and there is a steep ramp, very steep ramp. I have to climb out of it before I hit the level road, and after that there is no problem, I am going on a level road. But for that short interval of a few seconds, I have to face an exceedingly high load, and the torque that my motor delivers has to be able to overcome that. Another situation where this may happen is that if there is a undulating terrain and I find that I am inside a pit, and the pit is not very large but it is quite deep, and to just get out of the pit I have to deliver a very high torque for a few seconds, and once I am out of it I am fine. So these are all cases where I need to be able to overcome a much higher load than I normally face, but just for a few moments, for a few seconds. And another challenging context for a motor is when the vehicle is already going at a fairly high speed, and in front of my vehicle there is another vehicle which is going at approximately the same speed, slightly faster, slightly slower, but I want to overtake that vehicle and get ahead of it. Then again for a few seconds I want to rev up the throttle, speed up in a very short period of time and pick up a much higher speed and go ahead of this vehicle in front of me, and then move back to my lane, which is the same lane as the vehicle in front of me, but I have already covered a good distance in a few seconds, and then I can afford to reduce my speed. So this overtaking few seconds that I do it, maybe 10 seconds, 15 seconds, is a time when not only do I have to deliver a high torque for accelerating the vehicle, I have to do it at a high speed. So simultaneously the challenge of high torque at high speed is there. So these are all different combinations of torque and speed which are demanded by the vehicle from the motor, and the motor should be able to meet all these demands. So let us look at each of these. What is the demand on the motor in each of the driving modes? So if you look at the cruising at rated speed context, the rolling resistance is in operation. The rolling resistance comes into operation whenever the vehicle is running. There is air drag. We all know that air drag is significant when we are going at a reasonable speed, but if the speed is very low, the air drag can be neglected. Since I am cruising at a rated speed, I am not at a very slow speed, so there is a significant air drag. and I am going on a level ground, so there is no climbing torque required. I am going at a steady speed, cruising, so there is no acceleration torque required. So the total torque that is required is the sum of the rolling resistance and the air drag, and this torque should be delivered at a reasonable speed because I am going at a rated speed. Likewise, if I look at the peak speed context, I am going at the highest speed that I can on a highway. The rolling resistance is in operation, the air drag is much higher because air drag depends upon the square of the speed. If I go at 1.5 times the speed, the air drag increases by 1.5 squared, which is 2.25 times, and there is no climbing torque. I am going on a level ground. There is no acceleration because I am cruising at a constant speed, and this torque, which is now the sum of the rolling resistance and air drag, should be delivered at a very high speed. Then I told you about going on a family picnic to a hill station, and there is rolling resistance, there is air drag because I am going up the hill at a reasonable speed. I am not going at a peak speed, nobody drives uphill at top speed, and there is a significant climbing torque. There is no acceleration torque for the most part because I am going up at a constant speed, and this torque has to be delivered at the reasonable speed at which I am going uphill. The short steep climb is when I am starting from rest and trying to go over a steep ramp, and again rolling resistance is there, but because I am just starting from rest and I am going to finish this mode of driving as soon as I just get out of the ramp, the speed is very low, therefore there is no air drag, but there is a very high climbing torque, and in addition I have to accelerate the vehicle to pull it out, and so the acceleration torque is also very high, and this has to be delivered at a fairly low speed, not a very high speed, but by the time I come out of the ramp, maybe the speed is not very low, it is a little bit higher. So I have put a single green tick there. And finally, in overtaking, we have to overcome rolling resistance, we have to overcome air drag, there is no climbing torque, but there is an acceleration torque because I am trying to overtake the vehicle in front of me, and I am doing all of this at a reasonable speed, not at the top speed, but at a good speed. So now let us look at what is the impact of all of this on the design of the motor. So first we start with defining or understanding what is the kind of vehicle performance that we want. If I am designing a vehicle, I have to define the performance specs. If I am purchasing the vehicle, I can look at the website of the vehicle manufacturer and he would have described the performance that can be expected from the vehicle, and what you find is likely to look like this. So this is a vehicle which can have a load of up to 1000 kilograms. GVW, anybody knows what GVW means? What is GVW? Yeah, gross vehicle weight. Gross vehicle weight includes the weight of the vehicle and all the people and the luggage that is in it. The weight of the empty vehicle, what is it called? Curb weight, KERB. Curb weight is the weight of the empty vehicle, and the additional load that is going to be put on top of the vehicle in the form of either luggage or passengers, that additional load is the useful load which the vehicle is carrying. So what is that called? Payload. So the sum of the curb weight and the payload together is the gross vehicle weight, but as far as the motor is concerned, it does not care whether it is the payload or the curb weight, everything is a load, and the total load is what the motor should overcome. So I have just put what the gross vehicle weight is, and it must be capable of going up a gradient of 18%. The gradient can be described in two ways. We can either describe it in degrees or we can describe it as percentage. So, percentages for every length covered in the horizontal direction, how much is the height that it goes up, and the vehicle has a certain gear ratio, it has a wheel of a certain radius, it has a frontal area which will be important in defining the air drag, and while going up a long drive up a hill, then it will go at maximum 15 kilometers per hour. That is the description of this vehicle. When it is going on a level ground, its cruising speed is 50 kilometers per hour and it can go up to a peak speed of 60 kilometers per hour. This is the description of a vehicle. Now, from this vehicle I have to derive the specifications of the motor that I should fit on the vehicle. How do I do that? Actually, all that I need to know is F is equal to ma. If I apply F is equal to ma in a systematic way, then I can actually derive the entire specification sheet of the motor, and this may appear very challenging. How can a simple equation like F is equal to ma lead to such a detailed set of specs? This is what we will now go into in a step by step manner. So far, if you have any doubts, any questions, feel free to ask me and then we will move on. Any questions till now?